So one class of problems or one class of algorithms is sequence classification algorithms. In sequence classification algorithms, we have the data in the form of sequences. Earlier in general classification, we had the data in this tabular form. We had the data in this form. This was the data, and we have this different features, and we have the class labels. We have these as features, and we have these as labels, right? So we have for every instance of some training example, or suppose in this case we have words, so we extract the features and for each word, and then we give a label. Suppose we give the org label here, right? So this kind of data was required by the traditional machine learning algorithms, but in sequence classification we do require this kind of data, but we have the data in a sequence, right? So we extract the features, but we put the data in some order, right? So the order is maybe the sentence or the word order. So the order can be in the form of word order. So that means the sentence is starting with the word number 1. So the first training example will be the word number 1, its features, and then labels, then word number 2, word number 3, word number 4, and so on. So we do not disturb the order in sequential classification problems. So order of input is maintained in sequence classification algorithms. So what the sequence classification algorithms can do is that the algorithm itself can extract the data from the previous states, right? So in this way I am having this as a sequence of words. So this kind of information that is generated by the previous states, that can be accepted by the current states. Or if we have some kind of higher order sequencing, then we can also go to much previous states and then get the information from there, like this. So this is a second order Markov chain, right? So these are kind of classification algorithms which work in some kind of sequence. So one type of example we have is the hidden Markov model, which we did earlier some time back. So in this hidden Markov model, we assume that there is a hidden state that cannot be observed, and that hidden state is calculated with the help of some observed random variables. So in our case, the observed values are actually the words of some text, and their tags or labels are the states, right? So in this example of a POS tagging example, so chasing opportunity in an age of an uphill, so we see that these are the words that we can see, we can observe, but there is something hidden inside it. The hidden information is the POS tags. VBG is the word, NN is the noun, and IN is something like that. So we have these as the hidden information in these sequence of words, right? So we can have this kind of, this kind of structure for hidden Markov model. So similarly, we can apply the same technique, same methodology for named entity recognition. If this is the sequence of words for a named entity text, so Murdoch discusses future of News Corporation. We see that the hidden information in Murdoch is that it is some person, and News Corporation is some organization, right? So we can apply very successfully such kind of text data into sequence classification algorithms, and it is observed as well as it is proven that these sequence classification algorithms work quite better than the normal traditional algorithms, right? So we have different examples, like we have the hidden Markov model, we have the HMM. Apart from that, we have the conditional random fields. The conditional random fields sequence classification algorithm is actually an acyclic graph kind of structure, is having acyclic. In hidden Markov model, we have the directed graphs, directed acyclic graphs, but in case of CRF, we have the undirected acyclic graphs. So the structure becomes something like this. We don't have any directions, we have this kind of structure, and this structure is then actually modified into this kind of structure. So this one particular is now connected with like this. So this is the structure of conditional random field classifier. So we have these as the labels and these as the words, right? So this was a better algorithm than hidden Markov model, and suitably it takes less amount of training time than hidden Markov model. Now currently we do not have these hidden Markov model and CRF into these tasks, because we have more powerful neural network based algorithms like LSTM and all, RNN. So these are LSTM and RNN are also sequence classification algorithms. They actually look back into long sequences, and they can store information, they can discard information. So these are quite powerful. So currently we do employ these LSTM and RNN and mixture of all these algorithms into some sequence classification problems. So similarly, we can apply the named entity recognition task into these LSTM algorithms, and then we can see the results, right? So what is actually a simplest kind of a sequence classification algorithm? A simplest kind of sequence classification algorithm can be a conditional Markov model or a maximum entropy Markov model. It's more simpler than a hidden Markov model or a conditional random field model. So what we do is that we have these kind of data in which we can extract some kind of features. So this is actually the list of features that we can extract here. So we again get the same kind of table here that we got here, and then what we can do is that we can have this kind of architecture. We have this sequence data, we extract the local data, and then we extract the features, and then we generate a kind of sequence. So this sequence is actually, these are the states, these are the tags, and these are the features. Now what happens in case of this is the generalized architecture of a sequence classifier. So a simplest kind of sequence classifier is actually the Markov, the maximum entropy Markov model, in which we can maximize the entropy of the label. We maximize the entropy of the label of each state. right? So this optimization or this maximization can be obtained with some kind of optimization algorithms like gradient descent, or we have another method, a simple method that is called as Newton's method. And we have some kind of conjugate methods which for which, if for an expression we are not able to identify the gradient, we apply the conjugate method, in which we calculate or we uh, derive the conjugate pair of that expression, and then we take out the gradient, right? So conjugate means that if you are not able to maximize a problem, we identify some kind of expression which could be a kind of inverse or a kind of opposite which we can minimize. So if it is a maximization problem, we convert it into a minimization problem, or if it is a minimization problem, we convert it into the maximization problem, and then we can perform the smoothing. Smoothing, we all know, is a kind of improvement that could be applied when we obtain some kind of the expression. So we saw that Laplace smoothing have been applied in naive way. Similarly, we have different kind of smoothing algorithm that we can apply here also. So this is some kind of a general architecture in which, if we are doing the maximizing the entropy at each of these states, then we call it as a maximum entropy Markov model. So entropy is very simple, having a very simple expression, and it can be easily converted into, and this architecture can be easily converted into the maximum entropy Markov model. Okay. So that's all just theoretical concepts that are involved in the named entity recognition, and I hope you all have now acquired simple understanding of this topic. So we are done with this topic. Now we will start with